Okay, in this lesson, we're going to talk about the conic section known as the ellipse. We're going to talk about its definition, some of its characteristics and components, and then we'll work out a couple of example problems involving an ellipse and its equation. Let's start off with the definition. The definition of an ellipse says the set of all points in a plane whose distances from two fixed points in the plane have a constant sum. Okay, so looking at our diagram here, let's look at what that means geometrically. Here's an example of an ellipse here. We've got a center point. We've got two focus points that are on either side of the center. And notice it kind of looks like a squished circle. A circle is a unique type of an ellipse. We'll talk about that in class. But we've got our two focus points. This definition says that if you pick any point on this ellipse, so any point, I'm going to pick, let's say, a point right here. Then it says that the distance from that point to each of those two focus points. Okay, so if we look at that distance there, and let's call this D1, and we can call this D2. Weird, that is a scary looking dude. Let's see if I can fix that. Then the sum of D1 plus D2 is some constant K for every single point on that ellipse. So I could pick another point down here. Let's say this point right here. And if I, well, maybe let's try a different looking point. Point down here. And if I were to find this distance here and then add that to this distance here, even though these two segments are different, these two are different, then this plus this would be that same constant K. I might have to turn this video off if it keeps freezing. We'll see. All right. So I'm gonna get rid of these. We just need one of those examples. Backspace, delete, delete. There we go. All right, so now let's look at some of the components. So that's our basic definitions. The set of all points that have the same sum of distances away from two focus points. All right, so underneath that ellipse on your note sheet, we've got a list of components. Let's look at the first one, the center. Center is the intersection of the major and minor axes. So the center is this point right here. We can, it's already black. It's already colored in black. So let's give it a, so the center there. If you have colored pens or pencils or highlighters, I'm going to try to color code each of these components. Okay, video, I'm going to give you one more shot and then you're gone. Center in black. Vertices in yellow. Stay focused, Mr. Ford. The endpoints of the major axis are the vertices. So looking at that geometrically, let's see where our vertices are going to be. Our major axis in this example goes along here. So its endpoints are here and here. So these are our vertices in yellow, right, where our ellipse intersects our major axis. So what is our major axis? Our major axis, let's make that orange-ish. All right, so our major axis, all right. Say bye-bye, Mr. Flory. See ya. Our major axis in orange is the longer axis. It's the line segment of length 2A that has its endpoints at the vertices. Okay, so line segment length is 2A. So going back to our ellipse here, if we go from the center out to our vertex, so if our major axis is 2A, then that piece right there is just A. Okay, the distance from the center to one vertex. All right, now we can draw the other A here if we wanted to, but for clarity's sake, I'll just draw one. All right, so the whole major axis is 2A. All right, minor axis. Let's make the minor axis of this beautiful lima bean green. All right, it's the shorter axis, the line segment of length 2b that is perpendicular to the major axis at its center. So the minor axis goes through the center. Okay, so this would be our minor axis here. I'm going to draw the whole thing. And we've got intersections here with our ellipse. And then if we were to take the distance from the center to one endpoint, that is the length b. So we've got our minor axis, which is the shorter of the two. Our major axis is the longer. They both go through the center. The semi-major axis is half the major axis. All right, so that's the length of A. So we've already pointed that out. So maybe I should, let's go back. And I should color our entire major axis orange. And let's color just the semi-major axis. Let's give it a purple. So the semi-major axis in purple here, and that would be our length A. Okay, the semi-minor axis, if we give it maybe a pinker color, then the semi-minor axis, so that's just half of our entire minor axis. And that's length B. Semi-major, semi-minor. Make sure I get my colors coded. All right, next up, the latus rectum of an ellipse, or the LR. Let's see, let's go with red. Okay, so we'll call this the LR. A chord through the focus perpendicular to the major axis. Okay, it has a length of 2b squared over a. Circle that, that's important. Okay, here's our little formula to find the length of the LR. Okay, so it's a chord, meaning that it, just like a chord in a circle, it intersects the ellipse in 2 points, and it goes through the focus perpendicular to the major axis. So let's draw one of our LRs. I'm going to underline it here in red. All right, so through a focus perpendicular to our major axis. So here is an LR. Stops right there on the ellipse, and it is perpendicular to the major axis. Okay, and like it says here, it has a length of 2b squared over a. Okay, the eccentricity, what's going on? Bugging out. Eccentricity of an ellipse is E. All right, the eccentricity kind of describes how far away from a circle an ellipse is, or how oblong it is. You can think of it as the oblongity, if you want to make up a word. So it's the oblongity of an ellipse. Okay, the more that it, the closer E is to 0, the more it looks like a circle. The closer this E value is to 1, the more oblong it is. All right, and so we've got a little formula for E. E is C over A, where C is the distance from the center to the focus, and A is the distance from the center to the vertex. A is that same A, that's the semi-major axis. Okay, so we haven't labeled C, so let's do that. I've started green here, so let's maybe I'll circle C in green so we know what we're talking about. So C is the distance from the center to either focus. Both foci are the same distance away from the center, so it doesn't matter which one we go to. So that's C, that distance in green there. Okay, so notice if I were to draw C over here, then this C would be from here to the center, and it's got to be shorter than A. It can never be longer than A for an ellipse. Okay. Another interesting connection between these three since the minor and the major axes are always perpendicular to each other. Well, we'll get to that in just a second. I'm getting ahead of myself. All right, so let's look at standard form. Standard form equation for an ellipse. For an ellipse that is wider than it is tall, we've got x minus h squared over a squared plus y minus k squared over b squared equals 1. All right, so our equations for an ellipse will always have 1 by itself on one side of the equation, and then we've always got two fractions with a plus in between, x on one, y on the other. And then notice that underneath the x, we've got a squared, underneath the y, we've got b squared. Okay, to find our vertices, we can take, for the x-coordinate, h plus or minus a. For the y-coordinate, it's just our k. So this h and k looks real similar to the equation for a circle. The h and the k, again, that'll find you your center. So the center of our ellipse is hk, just like with a circle. And to find our vertices, it'll have the same y value. We'll just move it a units left or right. Okay, the foci, same y value as the center and the vertices. And to find the x-coordinate, we're going to move it c to the left or to the right of the center. The endpoints of the minor axis, since the minor axis is perpendicular to the major, then it's got the same x-coordinate as the center, but the y-coordinate we take k plus or minus b. Okay, so that's our horizontal ellipse. Maybe we should write that to the side there. So this is for horizontal ellipse. For a vertical ellipse, one that's taller than it is wide, then our formula has one important difference. Okay, we've still got the h, or the x and the y on top of two fractions. We're still adding. We've still got equals 1 on the right side of the equation. But notice the difference. Now instead of x being over a squared, x is over b squared. And instead of y being over b squared, y is over a squared. So all we did was we just switched the denominators. So one important thing to note is that our a squared value is always going to be greater than our b squared value. So that means since our 2a is our major axis, the major axis is always longer. So a squared is always bigger than b squared. So if our major axis is under the y, then it's going to be taller. If our major axis is under the x, as in our horizontal, it's going to be wider. Okay, so the center is still hk. Our vertices, in this case, since they are in line vertically with the center instead of horizontally, we're going to keep the same x-coordinate h of our center. We should rewrite that just so there's no confusion on if the center changes or not for a horizontal or vertical ellipse. To find the y-coordinate of the vertex or of the vertices, we take our k value from our center and then we add and or subtract our a value. Okay, and we get our a value from the square root of the denominator of the y fraction. The foci, again, we keep the x-coordinate of our center and we take the y-coordinate and we add or subtract our c value. Okay, so you might say, well, there's no c value in this equation. Where do we get that c from? Well, we get the c from something that looks a lot like Pythagorean theorem, but there's one important difference. So c squared, remember c is the distance from the center to a focus point. C squared equals a squared minus b squared. Notice the minus. That's the big difference from the Pythagorean theorem. For an ellipse, c squared equals a squared minus b squared. In our next lesson, when we talk about hyperbolas, then that's going to change back to a plus, and it will follow Pythagorean theorem. So star this, highlight it, underline it. In order to find C or to find A or B, if we know two of the other variables, then we're going to use this formula here. All right, and then the endpoints of our minor axis, we add and subtract B from our X coordinate of the center, and then use the same Y coordinate. All right, so let's look at a couple examples of how we're going to use this information to solve problems. So, example number 1, find the equation of an ellipse with a center at the origin, a vertex at 0, 5, and a focus at 0, 2. Sketch and label the vertices and endpoints of the major and minor axes. Okay, so I've got a little graph here. I find it really useful when you're doing problems with ellipses to, while you're working out the equation, to also have a graph going at the same time. Okay, they'll kind of help each other out if you do that. So if you have graph paper, or if you can sketch one out real quick, I think it's really useful when doing these all conic sections, really, especially ellipses. So I'm going to graph what I've got. Let's see, we've got the center at the origin. So I'm going to go ahead and plot that. So now in my equation, if my center is at the origin, if we start off with x minus h squared plus y minus k squared equals 1. Now, I don't know if my a or my b is going to go under my x or my y, so I'm going to hold off on putting my a and my b under there. But if the center is at the origin, then my center is at the point 0, 0. So if I plug in 0 and 0 into these two expressions, I'm just going to get x squared on the top of the first fraction, y squared on the top of the second fraction. Okay, so this is my h and my k. 0 and 0. So the vertex, a vertex is at 0, 5. So if I plot that point, going back to my graph, 1, 2, 3, 4, 5. So if my vertex is at 0, 5, and I have a focus at 0, 2, then that tells me, since my focus is in line with my center and my vertex, then my major axis is going to be vertical. So my A value is going to be underneath my Y. My B values are going to be underneath my X's. So we're going to have an ellipse that's taller than it is wide. All right, so if I go back to my graph, remember we've got two focus points. So this focus point is above the center. The other focus point will be the same distance from the center in the other direction. And the same thing with our vertex. The vertex, if it's 5 above our center, there's also going to be a second vertex 5 below our center. Okay, so that's all the information that they give us. They want us to sketch and label the vertices. So here's a vertex here, vertex at 0, 5. Here's another vertex here that's at 0, -5. And they want the endpoints of the major and minor axes. So the vertex is the endpoint of our major axis. So this line here from our center to that vertex, that is our value A. So that's 5 long. So if we wanted to plug that into our function, then we've got y squared over 5 squared, which is 25. So now we just need to find that b squared value. Okay, so in order to find that b squared value, we're going to need to use our formula that we just talked about that was important. This c squared equals a squared minus b squared. Okay, so let's set that up. I'm going to come down here a little bit. Okay, so if c squared is a squared minus b squared, let's plug in what we know. Our C value, remember, is our distance from the center to a focus point. So that's the length of 2. So I've got 2 squared, and my A squared is 25. I can pull that right from my formula, and I don't know what my B value is. All right, so let's solve for B in that equation there. Oops. All right, 2 squared is 4. Let's get b by itself, so subtract 25, we get a -21. It's negative b squared It's multiplied by -1, so 21 is our b squared value. For our formula, we can plug that right into formula for our ellipse. So now we've got x squared over 21 plus y squared over 25 equals 1, and that is our final equation for our ellipse. But now let's not forget to go back to our graph. We were asked to graph and label, sketch and label the endpoints of both vertices. So we got to do our minor axis here. So the square root of 21 is our b value. B is the distance from the center to the end of our minor axis. So let's see, square root of 21. 21 is between 16 and 25, so that's going to be somewhere between 4 and 5, the square root of 21. So somewhere between 4 and 5, I don't have to be too accurate as long as it's between 4 and 5. Okay, so there's my other two endpoints. So this guy here is going to be at the point square root of 21, comma 0. The other endpoint is at negative square root of 21. Whoops. Zero. Okay, so we've got our center, we've got the endpoints of our axes. We could sketch it now, but I'd like to get one more pair of points from our LR, from our lattice rectum. So if we go back to where we talked about that, we said that the LR of an ellipse has a length of 2b squared over a. So let's find the length of our LR. So it's 2b squared over a. So let's plug those in. We know that our b squared is 21. And our a value is 5. So we've got 42 over 5. 5 goes into 42 8 times. 2 left over. So our LR is 8 2/5 long. So that means from our focus, remember it's perpendicular to our major axis, we're going to go 8 2/5 long. But the center of our LR is at the focus. So we're actually going to go half of that. 4 1/5. 4 1/5 in the other direction. Okay, so that gives us 2 more points on our ellipse. If we do that to our other focus, then we've got 2 more points. So they kind of act as just kind of guides as to what our ellipse is going to look like. So if we were to finally sketch our ellipse, let's do it in red, then we want to make sure we hit all of those points. So from the vertex, it's going to look something like so. Okay. Real close to a circle because our A and B values were real close to being the same. All right, let's look at another example. So it'll be quicker. Number 2, find the equation of the ellipse with the center at the origin, vertex of 0, 4, and a minor axis that is 4 units long. All right, so I'm gonna plot what we've got. We've got the center at the origin, vertex of 0, 4. So that means we're gonna have another vertex at 0, -4. Our minor axis is 4 units long, so that means we're going to go 2 each way. All right, so if we start our equation, since our center is at the origin again, we're going to have x squared and y squared as our numerators. And to find our denominators, it looks again like we've got a vertical parabola. So our a value should be underneath our y, so this is our a value here, which is a length of 4. 4 squared is 16. Since they gave us the minor axis, remember our minor axis is 2b. So 2b equals 4, b equals 2, we want b squared, so 2 squared is 4. So we've got our equation right off the bat. X squared plus x squared over 4 plus y squared over 16 equals 1. All right, they don't ask us to sketch it, but if we wanted to give a sketch, we could do that real quick. Yeah, that's beautiful. Beautiful. Something like that. All right, let's do one more. All right, so let's say we're given the equation of an ellipse, and we're asked to find the coordinates of the center, foci, and the lengths of the major and minor axes. So we need to start with our equation here. Notice that our equation's in standard form. It's not in the vertex form. Did we call that standard form back there? I don't like that. Standard form. Let's call this expanded form then. So this is our expanded form. It's not in the form that standard form that we want for an ellipse. So let's put it there. We're going to have to use some of our completing the square skills. Let's gather our x's together. So we've got x squared minus 4x. Leave a little space. We've got our y's, so 9y squared plus 54y. And I'm going to go ahead and subtract that 49 from both sides to get it to the other side of my equation. Okay, so once we group our x's, we grouped our y's, we got our constant to the other side. Here's what it looks like. Now we can complete the square. So if we go in and let's say I'm looking for some value to add to this set of x's that'll give me a perfect square trinomial. So take your linear coefficient, cut it in half, so we get -2, and then we square that, and we get a +4. So we're going to add 4 to the left side of the equation. That means we need to add 4 to the right side to keep our equation balanced. Okay, go into our y's. Now I don't like this 9 coefficient here, so I might factor that out. So let's come down. Let's rewrite this down here. Let's go. If we go ahead and make this a binomial squared, so we're going to have x minus 2 squared. Okay, so let's factor out that 9. We've got 9 times y squared plus 6y. 9 times 6 is 54. -49 and 4 is a -44. Nope, -45. Okay, so now we want to complete the square here. All right, so let's do half of 6 is 3. Square that. We're going to add 9. Okay, but now be careful. We didn't just add 9. We added 9 times 9. So on this side, we're going to need to add 9 times 9, which is 81, to the right side. Okay, let's see what we get. We've got x minus 2 squared plus 9 times y plus 3 squared equals, and then a -45 plus 81. What are we going to get there? Let's see. 81 take away 40 is 41. Take away 5 more is 36. Let's try that again. All right, 36. I like the looks of that. Okay. Are we in standard form yet of an ellipse? No, we've got a couple things missing. First off, we don't have a 1 on this side. We've got a 36. And we also don't have fractions. Now you could say, oh, Mr. Four, we do. We've got them over 1. And that's actually true. So it's totally okay to have 1 as your denominators. If we just had 1 as our denominators, that would be a circle, which is a type of an ellipse. But one thing we can't have is, I missed. How did I miss? is that 9 there? Okay, we can't have a coefficient in front of our binomial with a y in it. So we're going to need to get rid of that, and we're going to need to take care of this 36. Let's start off by taking care of this 9 though. Let's divide everything in our equation by 9. All right, so I'm going to save space. I'm going to do it right here. Let's divide x minus 2 by 9. Let's divide this by 9. And let's divide 36 by 9. All right, so 9 over 9 is 1. 36 over 9 is 4. It's closer to 1. So we've got y plus 3 squared over 1. And we've got x minus 2 squared over 9. Okay, so we got rid of our coefficient there. We've still got a 4 over here. So to make that 1, you might think, well, we could subtract 3 from both sides, but then we're going to have some weird minus 3 over here. So the easier way to do it is to just divide by 4. So we're going to divide each of these by 4. So we can write it like that, 4 in the denominator. All right, let's see what we get. So we've got x, let's go up a little bit, x minus 2 squared over 9 times 4, which is 36, plus y plus 3 squared over 4 equals 1. Okay, so we got it in standard form. I like the looks of that. I like the fact that we've got perfect squares on the bottom. That'll make graphing it easier. Let's go back up and look at our directions. What are we asked to do? Okay, we haven't even started solving this problem yet. We've actually done the hard part first. I think getting it in the center form is the hard part. So now you're asked to find the coordinates of the center, focus, and the lengths of the major and minor axes. So now that we've gotten it in standard form, in your notes, go ahead and solve this problem. We'll talk about it in class tomorrow.